Hello, everyone. Good to see you all. Today, I'm going to be talking about the fundamentals of transformers, how they work. We're going to walk through a few examples of how to do that. For a more in-depth dive into a lot of the concepts that I'm going to be talking about here, there are a few classes that I've got on Skillshare that will also help you with the fundamentals if you want to dive in deeper. So I have an artificial intelligence for beginners courses on Skillshare that you can check out. There's how ChatGPT works. There's how to build a custom ChatGPT. A lot of those courses will help you understand the fundamentals of how to use what we're doing here. So today, the real goal is to break down a lot of these concepts into understandable chunks that we can use in the future. So why don't we go ahead and dive right in? I'm going to be sprinkling a lot of the content here with demos throughout. We're going to be using something called Modal. You can also use Google Colab, for example, but for now, we're going to use Modal. So I will get back to modal.com in just a second, but let's dive into how things work before I do that. Okay, so let's actually do the following. I'm going to... Okay, all right. So I'm going to bring up my backup tab here. Okay, all right. So what are large language models? How do they work? And how can we use them? So to really understand how large language models work, we have to understand how language models predict. Right? So how do AIs like ChatGPT actually produce many, many words? Well, to give you a rough idea, we have to produce words one at a time. So on the left-hand side here, we have the input. The input here is something called start of sequence. So this SOS right here means start of sequence. We want to begin some output. On the right-hand side, you have the output, which is just This is the first word of our sequence. And the middle, this black box right over here, is our LLM. It's our large language model. This is the AI. And this is producing words one at a time. Now, in your next step, you'll take the output that you produced from the first step, which is this A, and you add it to your input. Now your input is start of sequence and the first word you produced. And the output is the first word, and the second word list. Right? And you keep doing this. I'm going to take the last word of the output, add it to the input. Last word of the output, add it to the input. And we keep doing this. So now what you've got is a sequence of words. We've got start of sequence, a list of colors. We keep doing this until we finally get an output that's end of sequence. That means we can finally stop outputting words. But you'll notice that throughout this entire process, we only outputted one word at a time. So let's go back to the beginning here. What happened, right? We started from start of sequence, we produced a. Start of sequence a, we produced list. Start of sequence a list, we produced of. Right? SOS, a list of, we produced color. So on and so forth. So we only produced one word at a time. And in this way, you can produce an entire essay, a book, a bunch of code. You can do anything that the AI models have produced today. We call this autoregressive decoding. Right? This is what it means to produce outputs one step at a time. Uh-oh. I don't know if, I'm sorry. Let me try sharing screen again. Okay, all right. So now the, so at a very high level, we predict the next word. Our input is a sequence of words, and the output is just the next word that comes in the sequence. Right, so now let's show you a demo for how this works. So I'm going to navigate right back to, oh, well, there were the slides I was looking for. All right, so let's go right back to here. This is modal.com. So if you don't already, I'd highly recommend going to modal.com, set up an account, and you can create a notebook. Now, if you don't already have an account set up, don't worry. I'll share the code afterwards so that you can browse through and run the code yourself. But for now, the most important thing is just to follow along with the code that I'm writing so you can get a rough sense of how things work. At a very high level, the first thing that you always do when you're working with LLMs, let me actually zoom in a bit here just in case you can't see what's going on, is that we're going to use a library called transformers. Right? So this you've probably seen online in many, many different forms. I'm looking to my right, by the way, because that's where my screen being presented is. If you don't know code, don't worry. The rough idea is just to understand the takeaways for what's going on. I'll talk about these takeaways in a second. For now, if you do know how to code, though, you should follow along with what I'm writing here so you can get a firsthand feel of what it's like to actually run one of these AI models. So at a very high level, what I'm going to be doing here first is I'm going to be initializing my LLM. So here I've got an LLM. This is an old one. This is called OPT, Facebook's OPT. This is an open source model. What it means is that we can use its weights. And they are free for us to use. So in other words, this model right here that we're going to be running, this model that we're going to be running right here is actually free for us to run. We don't need to pay for a monthly subscription. We don't need to do, we don't actually need to pay every time the models run. This is for us to use. So let's go ahead and see. Oh, whoops, because I did this. Okay, all right, so now we've got this running. This is going to be downloading all the models for us while I continue talking for a little bit. So here, there are a few things in this screen that are pretty important for us. The first is we see that there's no GPU. So that's actually not a good thing for us. We should be running this on a machine with a GPU. So I'm going to switch this to T4, NVIDIA T4. So on the left-hand side here, click No GPU and click on NVIDIA T4. I'm going to click on Save Changes here. That's going to stop this code from running. All right, and now we're restarting. As soon as we restarted and we're on this new GPU, I'm going to rerun this code. We're still initializing kernel. Okay, perfect. So now at the very, very top, you should see a kernel running -T4. That means you have now started running on the NVIDIA GPU. So now I'm going to rerun this code. We're going to see a bunch of output just like we did before. It's going to be downloading this model. It's going to download that model. It's going to initialize that model, and then we'll be ready to use it. In our very, very next cell, I'm actually just going to start writing some code just so that we can get started with what we want to see. So I'm going to zoom in a bit further here just so that you can see more. Actually, maybe not. Okay, on the left-hand side, I'm going to minimize this window just so that there's more room here. And then I'm going to zoom in a bit more. Okay, perfect. So our model is already downloaded and is ready for us to use. We can double check that by just typing in one of those two variables, LLM, let's say. And once I hit Shift Enter, I get this output right here. So this means that our model has successfully initialized. All right, so now let's use this model. I mentioned before there's something called autoregressive decoding, which means we're going to be outputting models we're going to be outputting words one word at a time. So before I do that, though, let's abstract away those details and see how we can actually run predictions. Actually, the auto-generated output here is almost what we want. It's almost what we want, actually. So here we want to first define what our inputs are, right? So you can say whatever you would say to ChatGPT right here in this string. So I'm going to go back to a list of colors because this is what we had before for our demo. Right, so list of colors, and actually I'm going to need to do this. So again, if you're coding along and you're getting lost, don't worry. I'll share all this code afterwards so that you can run. The most important thing is just to kind of see how we're using these LLMs throughout this live session. All right, so once I've defined my inputs, the first thing that I do is I pass it into the tokenizer. To give you a very rough idea of what's going on, a tokenizer takes your input string and it chunks it up into a bunch of small pieces. At a very high level, you can imagine that it chunks up your string into a bunch of individual words. All right, so now that we've defined that input and we've chunked it up into a bunch of small chunks, let's pass it into our large language model, our AI. Okay, so now we've got max new tokens equals to 5. Max new tokens here says how many new words should this model predict. All right, so we're going to cap it at 5. We don't want this model to talk too much. Now, finally, once we've actually had the LLM produce outputs, the LLM produces, and we'll talk about this later, it produces integers that we need to translate back into words. And I'll explain what those integers are later. Right, so this for now is just a high-level overview. Okay, all right, now let's go ahead and run the model. And here we get the model's predictions. We get a list of colors, which is the original input we fed it. And then we got all the extra words that this particular LLM predicted, right? A list of colors and patterns for color. That looks like pretty sane English to me. It looks pretty interesting. All right, so just to recap, what happened was we had our inputs, right, which is this string right here, a list of colors. That was broken up into a bunch of small pieces. And each of those small pieces was assigned an ID. I'll explain what these IDs are later. But for now, let's just double check that's what happened, right? So this model inputs was a bunch of IDs like this. That was fed into LLM, which gave us more IDs. So let me actually show you what that looks like. Right, so generate IDs. This is, again, just a bunch of numbers. And you'll notice that these set of numbers match up, right? So the first 5 numbers here. So you can see, roughly speaking, that, I mean, not exactly, but kind of one of these numbers corresponds to each of these words. And we're one off, but that's an approximation, right? So we have, roughly speaking, a list of, and then maybe this is colors, for example. And same thing here, a list of colors, and then these correspond to the subsequent words the model predicted. Okay, so that's the inputs and the outputs. Now let's do some autoregressive decoding. So autoregressive decoding, as we mentioned before, is predicting step by step. So let's see that in action. I'm actually going to take our inputs, right? So input IDs. This is our inputs. Input IDs. And we're going to take our outputs, same thing as before, except this time I'm going to run it slightly differently. This distinction right here is actually quite important. We ran LLM.generate up here, and this masked away a bunch of complexity for how things work. It basically generated a bunch of words. One at a time for us. Now, if you look down here, LLM, this is now no longer calling the generate method. And instead, can't see screen anymore. Okay, so let me share my screen. Oh, I didn't realize how long they've been going for. Okay, all right. So I'm going to keep this screen open just so that I can see if there are any other issues. But back to here, we've got an LLM. Okay, so actually, I don't know how much we've missed. So I'm going to go back here. Okay, so what do we do so far? In the very beginning, we first initialize our LLM. Once we initialize our LLM, we generate some text. Now what we're going to do is we're going to generate this text, but manually. We're going to do this step by step so that we can see what's going on. Yeah, the editor is not visible. Okay, all right, so the editor should be visible now. Thank you guys for letting me know. Sorry I blabbed on for so long without noticing. Okay, all right, so now we've got the following. We're trying to reproduce what LLM.generate does, except we're going to do it manually so that we can see how we generate words step by step. All right. So the very first thing is, let's see what this outputs is, right? What does the LLM actually output? It doesn't actually output words for us, right? So let's see what that output is. All right, so oops, it doesn't like that we did this. We did, what was it complaining about? Oh, there we go, because I have this. Okay. All right. So this is the real output of our LLM. This is very far from what words are, right? So what exactly is going on? And what is this? Um, okay. So, all right, let's try this. Okay, perfect. All right. So what exactly is going on, right? Well, this is basically something that I'll talk about in more detail later. But for now, the most important thing is how to use this. Okay, so let me show you how to actually use this. I'm going to do the following. I'm going to take these outputs, and then I'm going to take the following, this. So the most important part of this line of code is to focus on the .argmax, right? We will treat this, all of this code right here, as just probabilities. These are probabilities over all the possible words in the dictionary. I don't know why this is, okay. So I'm gonna try something here to avoid the screen from flipping around like this. I am going to switch the screen that I'm actually sharing. Okay. All right. So let's do this now. Okay. All right. So I just shared my screen. All right. So here we got outputs.logits. And this is actually taking the probabilities of all the words. So what this means is, let's say I've got 3 possible words in my dictionary. This outputs.logis in theory tells us what is the probability of the first word, what is the probability of the second word, and what is the probability of the third word. When we take argmax here, what we're saying is give us the index of the highest probability word, right? So now if I take output equals to this, right? And then let's actually output what that is. This will give us a number of some kind, right? So it gave us some number 8. We don't really know what 8 means, but that was the idea so far, that this 8 right here corresponds to some word in our dictionary. So let's actually use this now. We're going to use this to, we're going to use this idea to actually get a word back out. Whoops. Okay. All right. Okay. So here we have output. Let's go ahead and write now the following. We want to convert this integer back into a word. All right, so this is output. All right, and now let's output that word. So here we got that the integer 8 was actually corresponding to the word and, right? So after all that, let's actually combine this piece of code with the ones above. Okay, so this entire process that we just went through, this is what the LLM.generate function up above was actually doing every single step, right? First, LLM produces a bunch of nonsensical numbers, which to us, now we know, means the probability of each possible word. Argmax right here means we take the highest probability word. Then we finally convert that integer back into a word, right? So this is the process that we're actually going through. All right, so now let's go to the next step. All right, so I've got reference code on the right-hand side here, which is why I keep looking to my right. I wrote up all this code before this lesson just to make sure that everything works first. All right, so now that I've got that, let's actually see what this looks like. Okay, so now I've got this blob right here. Now at the very, very start, this right here is just, okay, so actually I'm going to break this down a bit for us. Oops. Okay, so what are we going to do at the very, very beginning? At the very beginning, we're going to take all of the input IDs that we had before, right? So remember, our input was first it was a string, a list of colors. We chunked that up into a bunch of small pieces, and then we converted those into integers. And that's what this is right here. These are our integers. And again, don't worry too much about the code, just takeaways. All right, so the next step is once you have those integers, once we have those integers, we're going to then pass it into the LLM just like we did before. We're going to take the highest probability word, and then here's what we were talking about in the slides. This is probably the most important line out of all of this stuff that I just showed you. We're going to take the output we're going to add it to the input, and then we're going to pass the input right back into the model. Right. So again, I'll go back to those slides right here. Right. This is what we were talking about earlier. I'm just going to do this right here because it's easier. Right. So we started with start a sequence. We produced one output. We added the output to the input, produced some output, add it back to the input, and so on and so forth. Right. That's exactly what this step is doing. So let's come back to here. Right. We're doing the exact same thing here. We're adding the output back to the input. Now we do this 5 times because just like before, we wanted to produce 5 tokens. Right. And then finally, at the very, very end, we're going to convert those integers right back into words. And this is the exact input that we got before, a list of colors and patterns for the color. So we've actually successfully broken down how exactly LLM.generate works. Now, I've been talking a lot, so I just wanted to, I just wanted to see if anyone has questions about, what just happened here. Feel free to leave questions in the channel. I'll go back to that periodically to see if there are any questions. But we just reproduce what exactly an LLM does to regenerate text. All right. So now that we've done that, let's actually navigate right back to our slides. All right. So back to our slides right here. I'm going to open this up in full screen and slideshow. Okay, perfect. All right, so we just went through a demo for autoregressive decoding, and we're now going to instead talk about the next topic. Okay, all right, so this is what we talked about before. We produced a bunch of text one at a time, right, just like this. Now, there's actually a second step here that I wanted to show you. And so I jumped to the conclusion here a little bit too quickly. There's a second way of actually producing outputs. And this is actually really key. I'll show you why this is one of the biggest confusions about how LLMs work. On the left-hand side, I have a prompt, right? And a prompt here means something that, say, you as a user passed in, right? So you went to chatgpt.com and you said, ChatGPT, please give me a list of colors. Right? Let's say that's what this left-hand side it says, right? It says, give me a list of colors. Now, the first thing that the LLM needs to do is it needs to process that input somehow. So just like before, when we say an AI processes something, what it usually means is we run the input through the model, right? So here, we're going to take that input, which is give me a list of colors or just a list of colors. We pass that as input, and the output seems like nonsensical, right? If you look at this right-hand side, it says I lot of the and what does that mean, right? This is total gibberish. And even for a state-of-the-art model like the ones that OpenAI is serving, the model will still do this. It'll still give you something that kind of looks like gibberish if you just read it from first word to last, right? So what's going on here? Clearly, ChatGPT doesn't give us gibberish. So how does this work? Well, we need to read it in a slightly different way. We need to read it just like we read the text before. Instead of going down all the outputs and going from first word to last word, we need to look at the left-hand side. Look at the input first, right? The output that's produced actually corresponds to 5 different sequences of output. It corresponds to the first word of the input and then the first word of the output, right? So start a sequence, I. The second word of the output corresponds to the first 2 words of the input and then the second word of the output, right? So the way to read this is start a sequence, a lot, right? Start a sequence, a list of the, and then a list of colors and, right? That's the proper way to read this output. And given that, all of a sudden the output makes a lot more sense, right? We call this prompt processing. Prompt processing means you feed in a bunch of text and you pretty much get a bunch of outputs that correspond to the next words that we just saw, that you have to read it in this specific way. Now, before, autoregressive decoding, remember, was just producing one word at a time. This is producing basically, so if I have n input words, prompt processing produces n outputs. Okay. So we have 2 possible ways of calling the LLM. We have prompt processing versus autoregressive decoding. Prompt processing, remember, is pass in n tokens, get n tokens out. Autoregressive decoding basically means we're going to take some input, feed it in, take the last output, add it back to the input, and keep doing that repeatedly, right? Okay, so if that's confusing, feel free to leave questions in here. And I also talk about this in more detail in the Skillshare classes I talked about, just in case that is confusing. Okay, perfect. All right, yeah, thanks for everyone for chiming in when slides are missing. Okay, all right, so this is what we talked about so far. We've talked about how to use the entire LLM as a black box. Right? We have some input words, and we produced the next word. Now, what we haven't talked about is what goes into that black box, like what is in this gray box right here. So let's break that down now. Right, so we have 3 parts, actually, of the model. The first one is to convert words, right? Like let's say the word is you, and when you convert that into vectors. Now, what are vectors? Vectors, I'm going to avoid a technical definition here. Vectors are just a bag of numbers for now, right? So we're going to convert words into bags of numbers. That's the very first step. Now, yeah, so I just said earlier, vectors are just a bag of numbers, right? And if you're a coder, then more formally, vectors are arrays of numbers. So yes, there's an ordering to these numbers. All right, so let's look at a few of these vectors, right? Vectors for words will look something like this. Let's say that green right here, 0, 1 is one word, 0.7 is a different word, and 0, -1 is another word, right? What I realize is that I actually might have some notes here for things I wanted to mention. I just wanted to make sure that I'm mentioning everything that I did want to. Okay, anyways, let me keep on blabbing while I'm doing this. So here we've got a bunch of vectors, right? These are just arrays of numbers. And each of these corresponds to a single word. Aha, I knew it. I did have notes that I wanted to say for certain. Okay, so now let's understand, how do we visualize what each of these arrays means? So let's go here, right? So the first method is just to treat these arrays as coordinates, right? So each of these arrays has only 2 values. We'll say the first one corresponds to X and the second one corresponds to Y. So we can plot these words here as if they were coordinates. But you can also consider these points as arrows pointing to those points. So let's visualize this instead as vectors, right? So these are vectors, basically points that start from the origin and end up at 0, 1, 0.7, or 0, -1. All right, so to simplify, I'm going to sometimes refer to vectors as just points. But really, they're the same thing. They're either the arrow starting from the origin going to that point or just the final point. All right, so now let's visualize vectors. So what we did before was we visualized vectors as points or direction with length. All right, so now let's connect these back to the words, right? So from before we said the first one, U corresponds to 0, 1, let's say, and maybe we say that R corresponds to 0.7 and cold corresponds to 0, -1. These are completely arbitrary mappings, but basically words correspond to bags of numbers. All right, so that's the first step here. The first step here is to convert words like U into vectors. All right, for now, 0, 1 is just a random word. We're going to make sense of this in just a second. Right? But for now, let's finish this diagram first, and then we'll make sense of what does 0, 1 mean. And
Alvin, we can't hear you.
Oh.
I mean, sorry, we can't see you. The screen.
Oh, okay. Thank you. Yeah, sorry. Okay, entire screen. Okay, perfect. All right. Perfect. All right, so we've converted our words U into 0, 1. Okay, so actually, I don't know how. Yeah, thank you. All right, so here we got U converting into 0, 1, right? Okay, so next step, we now want to transform those vectors, right? So for now, let's leave how transformation happens in sort of vague terms. Just for whatever reason or through whatever mechanism, we go from 0, 1 into some other combination of numbers. Right? In this case, we went from 0, 1 to 1, 0. I'll talk about how that's done later. And like, okay, so let's actually go back to here. Okay, so I realize I need both these open so I can tell when the screen disappears. Okay. All right. So right now what we did is okay, so let's recap. We went from U, which is a word, to a bag of numbers. We went from that bag of numbers to a different bag of numbers. But now we need to convert that second bag of numbers, 1, 0, back into a word. So how do we do that? How do we convert that into a word? So let me explain how this is done by visualizing once more. And again, we're just going to be visualizing vectors as points, right? So 1, 0 is just the point 1, 0 on our diagram. All right, so how do we convert this back into a word? So let me show you this step by step. Let's say that you had the 3 words from before. You had you, are, and cold. And these are also all plotted as just points on our diagram, right? Well, to convert our new vector, 1, 0, we simply look for the closest word, which in this particular case, we look for the closest word, which as you can see here is just R, right? R is the closest word to 1, 0. And so that's roughly the idea. To convert these arrays or these vectors back into words, look for all the words in your dictionary and see which one is closest. So at a very high level, this is a nearest neighbors, right? So let's go. All right, so let's visualize these 3 steps, right? In the very first step, on the very left-hand side, we went from a word to an array of numbers. That's called embedding. Then we went from an array of numbers to a different array of numbers, and that's a transform. And then the last step is to go from our array of numbers to a word, and that's nearest neighbors, right? We're going to go through each of these steps. We're probably not going to finish all these steps, but I wanted to show you the most interesting one, which is probably this first step, embedding. All right. And also, for what it's worth, I'm just sharing these slides afterwards, so you will have access to these slides in the event that I don't finish all of them. All right. So let's do the following. So just to recap, oh, dang it. Yeah. Haha. So now I'm on top of this thing, breaking every so often. Okay. Oh, yeah. Okay, so the first step here is to go from a word, which is U, to a coordinate 0, 1. Then we transformed it into a different point. And we said, what does this point mean? Well, we simply plot all the words, and then we looked at the one that was the closest, which is R. So we simply say that our output is R. All right. So now that we've done this, let's go ahead and see how to actually understand these embeddings more, right? Like, what is 1, 0? How do we know that, cold corresponds to 0, -1? Right? How does that happen? So let's actually show this. Let's see what happens. All right, so back to our code here on modal.com. I need to pull up this. Okay, perfect. All right, so I'm going to import a few different things first. So this is just setup, not super important. What we're going to show you is how to convert these words into embeddings, and then what those embeddings mean. So the first thing to do is I'm going to be downloading something called Word2Vec. I can explain this if folks are interested, but it's maybe not the most important thing at the moment. Okay, so I think the problem is that this is not here. Okay. Sure. Okay. All right. So we need to install a few things. I didn't realize that we had to install these. Once we've got these installed, oh, that's right. Yeah, we did have to restall. Okay. All right. So now that I've installed them, I'm going to restart my kernel. All right. Notebook kernel is restarted. Now that we've done that, I'm going to run this cell. All right, perfect. So this should now be downloading. Okay, so what am I downloading? I'm downloading okay, that was pretty fast. I'm downloading the mapping from words to arrays of numbers. In other words, from words to vectors. And that's how this name comes about. It's called Word2Vec, right? So I'm downloading this mapping, and now we want to use this mapping. So let me show you what each word corresponds to. And it's going to look like gibberish at first, but bear with me there. I'll explain why this gibberish actually has some sense. So here we're going to construct a regular Python. Actually, we're not going to do that. We're going to first, okay, there we go. So you know what? I'm just going to take my sample code. All right, so here, oops, yeah. All right, so this is the code that I was working with. Okay, that's not, I don't want the auto-generated code. All right, so the first thing that we do here is we're actually going to download a specific data set. I'm using a subset of the dictionary, right? So I mentioned before, we're downloading a massive dictionary mapping from words to vectors. I'm going to be doing just a subset of that, just because we don't need the entire dictionary. So these two things right here load that conversion. This will allow me to convert any word into a vector. All right, so once this is done running, then we'll be good to go. And then I can show you some cool stuff. Okay, so the first thing I'm gonna do right here is I'm going to use this model. The way to use this is just like any other Python dictionary, except model under the hood converts this into an array. Right. All right, so let's actually see what king looks like. And king is a very, very long vector. It's got a lot of numbers associated with it. We're only going to look at the first 10. Okay, so it gave us 10 numbers. That's great. But like, what do these 10 numbers mean, right? Okay, so now let's do something crazy. Okay, so if you've heard of word2vec before, and if you haven't, that's okay, even better. If you have heard of it before, though, you may have heard that you could do some interesting things, like the following. You could do, let's say that we convert man into a vector. We convert woman into a vector. And now we can do some really weird arithmetic. I can actually say the following. I can say king minus man plus woman. Right? So if we look at this line, it makes no sense that you can subtract and add words. But since we converted all of our words into vectors, now, we kind of can do this, right? We can certainly add and subtract numbers. But if you think about what this means linguistically, right? King minus man plus woman, we kind of know what this should give us. So let's actually run that. Now we're going to do the same process we did before. So what have we done so far? We converted words into numbers. We did some kind of transformation. Obviously, this is not a large language model. This is just us transforming words. But the large language model would do something fancier here. But for the last step, we need to convert these bag of numbers, these vectors, back into words. So let's do that, right? We need to do nearest neighbors, basically. All right, so I'm going to, again, just take my blob of code. Okay, so this is the blob of code. We're going to first compute the similarity. The similarity between between all possible words in the dictionary, which is model.vectors, with our current result. This is the current vector. Okay, I did catch that. Okay, we're going to compute the similarity. So this is the distance, right? Or the inverse of the distance. Now we're going to sort by distance. Right, so again, similarity is just the negative of distance. So this right here is actually our distance. So we're sorting by distance. And then here's what we're going to do. We're going to say for all of the words in our dictionary, and I only took the top 3 because I'm only taking the 3 closest words. Right? And for each of the 3 closest words, as long as those words aren't one of the original king, man, or woman, I'm going to print that out, right? So watch this. I'm going to run this nearest neighbors, and you get queen. And that's the absolute crazy part. King minus man plus woman, linguistically, should give you queen, right? And we can do this multiple times with other words. So let's see that in action. We're going to do this now. Before we do that, though, there's actually a nice method that we can use called most similar, which just does the above. I wanted to do this manually so that you can see what's going on underneath the hood or under the hood. But you can simplify a lot of that code by just doing this one line, right? You can take the words that you wanted to add and the word that you wanted to subtract. So this right here technically corresponds to king minus man plus woman. All right, and again, this will give us queen. All right, so let's try a few other ones. So now we're going to try, let's do Paris minus France and then plus Germany. Right, so this is Paris minus France plus Germany. Right. Okay, it was key error. Okay, so it looks like these, oh, I see, because I need to capitalize this. All right, there we go. So now we've got Berlin, right? So it's actually insane that all of a sudden we have a way to add and subtract words, which is a crazy statement that would have made no sense if I'd said this, maybe like 10 minutes ago. But now, like, you know exactly what this means, right? So let's try a few more. We can now do, I'm gonna look at my notes this time so that I do things that I know are valid. So I also previously did cat. Okay, so cat minus feline, feline, plus canine, right? So cat minus feline plus canine, right? And we get dog. So try a few of these examples yourself if you're following along. If you're not, don't worry. I will share this notebook and you can try more yourself. But this is a really cool thing. This means that all of a sudden, like words have, word addition and subtraction have linguistic meaning. Now, I'm going to do something else, though. We can also take averages. So let's say that I didn't do any negatives, right? So let's say that I just did positive. So I'm going to remove this, and then I'm going to do breakfast, lunch, and dinner. So underneath the hood, this is basically breakfast plus lunch plus dinner. And technically speaking, there's actually a divide by 3 in here. So it's basically taking the average of these 3 words. All right, so this gives us meal, right? So averages make sense, which means division makes sense, right? So addition, subtraction, division all make sense. And we can also do one more right here. Since we're talking about kings and queens from before, let's just take the average of king and queen, right? And then we get monarch as expected. So king plus, or let's just say average, right? Because that's actually a more accurate reflection of what's going on under the hood. And then we're gonna do the same thing here. This was average of breakfast, lunch, and dinner. Okay, all right. So these are word embeddings, right? The word embeddings have a lot of meaning to them. And so that's why we can do simple arithmetic to actually, that's why we can do things like this to transform our input. Now, LLMs clearly don't do something as simple as this. They don't just add or subtract, and certainly don't just take averages of the input. But as a very start, this is a key idea. So really quickly, oops, that is not the right one. So let's go to here. I just wanted to make sure. Okay, all right. So let's go back to our slides. We've got the very first part of our demo down. There's another part of our demo that's also very, very important to see. So to recap our 3 steps, we went from a word to a vector. We transformed that vector and went from a vector back into a word, right? Those are our 3 steps. Let's dive into more of what this transformation is, right? We dived into what the embedding was. Let's talk about the transformation. So how transformers predict? You've heard a lot about the word transformer possibly, and transformers are just the building blocks of these large language models, right? Transformers are just this blue box right over here. All right, so let's talk about what's in that blue box. Well, here we start off with a bunch of, here we start off with a bunch of words, right? This is after, or this is the dictionary that we were talking about earlier. Okay. Let's reshare these slides. Okay, let's reshare. All right, so these are all the words in our dictionary, right? We had 0, 1, 0.7, 0.7, 0, -1. Now, what we're going to do is the following. We're going to compute distances between these, right? And you might think, distances are pretty straightforward, but I'm going to do something different, which is inside of our code, if you notice, we had a something dot something, right? So I'm actually show you that again. If I go back into my code, right over here, we did something weird. I didn't actually compute distances, right? I did model.vectors, which is all the possible words, and I took a dot product with our final, the output of our transform, right? So the output of step 2. So I took a dot product, and let's understand what is a dot product, right? So I want to visualize that here. Let's go back to here. All right, so here we have a bunch of these vectors. Let's take dot products between them, right? So if I take a dot product between blue and green, then we get 0.7. Between blue and purple, we get negative 0.7. I think, yeah, these are actually correct. And then the dot product between green and purple, right, which is -1, yes. Okay, so don't worry too much about how to actually do this dot product. The most important thing is that these numbers give you a sense of how similar these 2 points are. -1 being the absolute most unsimilar, right? It is literally the opposite direction, right? 0.7 means that your points are pretty similar. It's these two right here, right? They sort of correspond to each other. And then -0.7, right? They're not as opposite as purple and green are, but they're pretty different as well. All right, so at a very high level, dot product gives you a number between -1 and +1. With some caveats. It gives you a number between -1 and +1, and it tells you how similar these two things are. All right, so dot products tell us how similar vectors are. And I've got this asterisk right here. Don't worry about it. But pretty much, it's not always going to give you -1 to +1 if they're not unit norm. And unit norm just means that they all lie on this unit circle. If that didn't make sense, don't worry, just ignore that. Basically, dot products tell us how similar vectors are. All right, so now let's actually explore some of these dot products. And this is the second cool part. We can do other transformations besides just add, subtract, and divide. All right, so let's actually see some of these dot products. Now, okay, so let's actually do a few right here. So we've been talking a lot about cats and different countries and monarchs. Let's try, actually, we can do that again, but let me show you one that I got here first before I go off script. Okay, so here we're going to convert orange into a vector. We're going to convert apple into a vector. And then we're going to convert dog into a vector. So intuitively speaking, if you look at these three words, which ones are supposed to be more similar, right? Well, we expect orange and apple to be very similar to each other, and we expect dog to have like no relevance whatsoever, right? So let's convert all these into vectors. Now let's see if our intuition matches what the dot product tells us. So here I'm going to do dog. Oh, actually, let's do orange and apple first. Okay, so we're going to do a dot product between orange and apple. And actually, just to be consistent with what we had before, I'm going to do it this way, right? Okay, so orange dot apple. And it gives us some number, like 0.4. We don't really know what 0.4 means. We have to look at other numbers to understand their relative values, right? So the most important thing is that the similarity between orange and apple is higher than the similarity between apple and dog, right? So let's check that. So we're going to do apple dot dog. Right? And indeed, that is true. Orange and apple are way more similar than apple and dog. And let's do the same thing with orange now. Orange dot dog. Right? Same thing here. So I don't know why apple is more similar to dog than orange is, but whatever. That's not really the point. The point is that orange and apple are way more similar than apple is to dog or orange is to dog. Right? So that's the intuitive understanding of dot products in this word space. Right? Okay, so we can do a lot of stuff. Basically, once we convert our words into vectors, we have a lot of very interesting things that we can do. We can add, subtract, divide, take the average. We can even do these dot products to tell how similar two words are. Right? So all of these are sort of the unit operations, the basic atoms of how to build an LLM. Obviously, we're not going to break down an LLM into like millions of these operations manually, but as we're building an LLM, keep in mind that this is what makes an LLM work, because all of this math has semantic meaning. It has linguistic meaning, right? Okay, right. So I definitely way over prepared too much content for this hour, but I did want to talk about a few more concepts. Okay, so let's go back into our slides. Okay. So we've talked about dot products, addition, subtraction, and whatnot. Most of our focus here has been on how do we take words and how do we do something meaningful with them, right? Now, I'm going to introduce one concept here in this last 10 minutes that you've probably seen before and that needs a lot of demystifying. right? So in the transformer, you may have heard of something called self-attention. I'm going to explain what that is. So the rough idea is that some words change meaning based on other words, and we want to capture this somehow, right? So in order to do that, we're actually going to use something called self-attention. Okay. All right. So some words change meaning based on other words. Here's an example. Let's say we have cold, right? Cold could, if we have feel cold, then we know that cold means not warm. If you write a cold, then it's likely that cold means sickness, right? So we want to understand, based on context, what does cold mean? And cold kind of meaning that is changed by the words around it. Okay. So we need basically different vectors for each meaning of cold, right? So we need different arrays of numbers that correspond to each meaning, because otherwise we would not be able to tell the difference between these two versions of cold, right? So knowing that, we want to actually dive into the transform operation right here and make sure that we have different representations for these two meanings of cold. All right, so let's say that we start with cold on the left-hand side right here, right? Cold is first converted into an array of numbers. And before we look at other words, that transformation alone is going to be the same regardless of what cold means, right? Cold has just one transformation into a vector, and then we need to make some manipulations, right? So feel will also be converted into some vector. Now, the transformer is made up of two steps. The first is called self-attention. That's what we're going to be talking about, and that's how we're going to incorporate multiple words meanings. The second part is called multi-layer perceptron. In that particular part of the model, we're going to modify words individually. We're not going to get to that part today, but also that part has a lot less intuition for what it's doing. So we are going to focus on self-attention for now, and that is probably the most confusing and the most unique part of a transformer. All right, so self-attention at a very high level, we're going to somehow incorporate context. Right? We're going to somehow allow each word to modify all the words around it. Nice, that's self-attention right here. All right, so let's talk about what does self-attention do? So first we converted feel and cold into vectors, and now we're going to run self-attention. The first thing that we can say at a very high level is, let's say that we just took our inputs and we took their average. Right? Like we said before, average has some meaning, right? Well, this has some problems. Okay, so yeah, okay, I'm gonna see how much I can get through here. So basically, if you take the average, now regardless of what happens, the outputs are all going to be the same, right? So instead of feel cold producing the next words, like we said before, or we're just gonna have the same word in both positions, and that's not good. So instead, we're going to take a weighted average. I haven't talked about how we're going to compute those weights, but at a very high level, this is all self-attention is doing. All the fancy mechanisms we're going to talk about is just a weighted average. Okay, so I did have a demo here. I don't know if I'm going to actually have time to fully do that. Let's see. Okay, yeah, I'm definitely not going to have time to do that. Okay, all right. So I will share this notebook afterwards so you can see how to build this self-attention manually. And that can help actually elucidate a lot of what's happening behind the scenes. But for now, at a very high level, self-attention is just a weighted average. Okay, so really quickly, I'm going to talk about what the multi-layer perceptron is. I think breadth is probably better than depth in a single place right here. So here, for an MLP, you want to modify words individually. So I'm going to illustrate that here with some green, right? So this green part right here, the MLP, we're going to pass in each word individually, and each of them on their own is going to be transformed into a different vector, right? So this illustrates our process so far. We went from an input to a vector. The vector, we added some context. We added some context using self-attention. Yeah. Uh-oh. I don't know why. Sorry, let's wait for the slides to come up here. Okay, all right, perfect. So on the left-hand side, we have words that are converted into vectors. with self-attention, we somehow modified all the words using all the other ones, right? Using a weighted average. Then we passed it through some operation that we call the multi-layer perceptron to finally transform the word, right? And then again, I'll show you code for building an MLP manually. Wait, okay, so we don't have time for that either. Okay, all right, so at the very, very last step, then we'll finally convert those vectors back into the original words. Okay, so in this sense, we've actually talked about the entire LLM from start to finish already. Its major 3 steps, and at a very high level, how this transform works. You've also gone through the intuition of like why transforming words, adding, subtracting, taking the average of these words even makes sense to begin with. Yeah, and we've got 5 more minutes, but I realized that after this, we dive into some other concepts. I won't really have time to finish. So I'm gonna actually pause right here, maybe end right here, and then let's start some Q&A. So I'm gonna go through and start looking at the questions that folks have asked, and yeah, please ask me more questions. So I'd love to answer questions for you. Okay, all right, so let's talk through these. So what happens if when the meaning, okay, let me actually drag this here so I'm actually looking at you guys. All right, so what happens when the meaning of words is completely irrelevant? So that's a very good question. And I'm assuming you mean in self-attention. So in self-attention, right? So what happens if the words are completely irrelevant? Then a weighted average or just an average would end up possibly polluting, that word's vector, right? So the weights in our weighted average kind of account for this. The rough idea is, so from before, we mentioned that we took the dot product between orange and apple and between apple and dog, right? So although like this isn't entirely the case, but roughly speaking, the dot product tells us if these 2 words might kind of influence each other's meaning. I know that's kind of hand wavy and it's not exactly true, but at a very high level, you can think that the weights of the weighted average come from those dot products, right? So in other words, if 2 words influence each other's meaning, then they'll be incorporated into the weighted average. Okay, so that is the high level. Now, next question is there a connection between flash attention and self-attention? And that's a really good question because this is pretty related to my active area of research. So I will, I actually don't know okay. So anyways, let me explain what this is at a high level. Flash attention is just one way of running self-attention super, super quickly. And the best way to explain this is large language models are obviously like they're billions of parameters, they're massive. And the reason why running them is very slow is sometimes not because there's a lot of math to do. It's not because there's a lot of adds or subtracts or multiplies or divides. It's actually because it takes a lot of time just to move the weights of the model around, right? So just to explain really quickly what I mean by weights of the model, remember from grade school, we had y is equal to mx plus b for the equation of a line, right? X was our input, y was our output, and m and b in our line were the parameters of that line, right? If you changed m or b, if you changed the slope or the y-intercept, the line would completely change, right? That was a model. And the parameters or the weights were m and b because that dictated what the model did. So in the LLM case, we have a bunch of m and b's. We have billions of them. We have many, many parameters. And sometimes just loading those parameters so that we can do math with them is way slower than actually doing the math itself. Right? So flash attention sort of decreased the number of times you need to move those parameters around. Right? And that was why flash attention was so fast. I actually talk about this in more depth in a blog post. So yeah, I guess I'll link to this later if it's possible to link. But for now, at a very high level, flash attention is the fast version of self-attention. Yeah. Any other questions that folks have? Okay, looks like we're roughly right on time. So maybe let's, yeah, so let's move on then to the very, very last portion of this. Basically, if you did follow along, and even if you didn't, I'll share this notebook afterwards. Definitely share anything that you do with the notebook. I think the most interesting things, the biggest aha moments will actually be changing how you like what we did with the pluses and minuses, with the averages and so on and so forth. Those would be so those would be the most important things to play with. Once you've done that, you can post what you've learned or what you tried, what you added or took the average of on Instagram at Skillshare and use the hashtag Skillshare Live. Yeah, and make sure to add your prompts and results to the project tab on my classes over at Skillshare. All the links and handles are down in the caption in case you missed them. And make sure to subscribe to Skillshare's YouTube channel for more live sessions like this one. Yeah, so thanks for tuning in. Can't wait to see those projects. Yeah, like I mentioned before, if you want to learn about any more of these things that I talked about in more detail, definitely check out Artificial Intelligence for Beginners, how ChatGPT works, or how to build a custom ChatGPT. And I'll walk through these concepts a lot more carefully in those lessons. But yeah, definitely look forward to seeing those projects on Skillshare. And yeah, thanks for tuning in, everyone. AI won't take over everything. So I don't think it's a matter of how long. I don't think it's going to happen. You know. All right. Yeah. Thanks, everyone. Thanks for joining.